Hello viewers, in today's session we are going to discuss two important problems related to linear differential equations of this type, that is dy over dx plus py is equal to q, right? So whenever we have a differential equation of this type, then this equation is known as a linear differential equation of first order and first degree, right? So the order and degree of this differential equation are both 1, right? And here p and q are either constants or functions of x. So p is either a constant or a function of x, and similarly q is also it may be a constant or it is a function of x, right? So whenever we have a differential equation of this type, the first step is to find out the integrating factor, right? So let us denote the integrating factor by the abbreviation that is if, and the integrating factor of this differential equation is given by this expression that is exponential, and here we have e raised to the integral p dx, right? And the solution of this differential equation is given by this expression, that is y times the integrating factor, and then we have the integral, then we have q times the integrating factor, and here we have dx, and c is the constant of integration, right? So these two steps are important while solving a linear differential equation of this type, right? So p and q are constants or functions of x. So first we'll find out the integrating factor, which is e raised to integral p dx, and then the solution is given by y times the integrating factor equal to integral q times integrating factor dx plus c. C is the constant of integration, right? So when we solve these two equations, the first step is to reduce these equations in this form, right? So let us first solve equation number 1. So let us first write this equation in this form. So y prime can be replaced by dy over dx. So we have here dy over dx, and then we have 2xy, and here we have x square e raised to minus x square, and here we are given a condition that is when x is equal to 0, then the value of y is pi, right? So first we'll find out the general solution of this differential equation, and then by using these initial conditions we'll find out the particular solution, right? So now if we look at this equation and this equation, then we can see that this equation is already given in this form, right? So here we have dy over dx, then we have py. So here the value of p is 2x, and then we have q, and the value of q is x square e raised to minus x square. So p is 2x, which is a function of x, and q is given by x square e raised to minus x square, which is also a function of x. So we can now claim that this equation is of this type, that is, it is a linear differential equation, right? So let us first find out the integrating factor. So the integrating factor of this linear differential equation is given by e raised to integral p dx. So p is 2x and dx, and we can now write 2 times the integral x dx, and we have 2 times here we have integral x dx. So the integral of x is x square over 2. 2 and 2 get cancelled, and here we have simply e raised to x square, right? Okay, so now the solution of this differential equation is given by y times the integrating factor. So integrating factor is e raised to x square, then we have integral q. Q is x square e raised to minus x square times the integrating factor, which is e raised to x square dx, and c is the constant of integration. So we have y times e raised to x square, and here we can see that we have x square e raised to minus x square plus x square, right? So applying the laws of exponents, and we have c, right? So this is y e raised to x square, and we have here integral x square, this is e raised to 0 dx plus c, and this is e raised to x square, and we have e raised to 0 is 1, and we have x square times 1 is x square, and the integral of x square is x cube over 3, and c is the constant of integration, right? So we can now write this expression as x cube over 3 times e raised to minus x square, and then we have c times e raised to minus x square, right? So taking e raised to x square in the denominator of x cube over 3 plus c. So here we have the general solution of this differential equation as y is equal to f of x, right? So we have expressed y completely in terms of x, and the solution, general solution, is x cube over 3 e raised to minus x square plus c times e raised to minus x square, and here c is some arbitrary constant, right? So to find out the value of the constant of integration, let us make use of this initial condition. So we have x is equal to 0, y is equal to pi. So substituting these values in this general solution, we have pi, y is pi, then we take x is equal to 0, so this entire term is equal to 0, and then we have c times e raised to 0 because x is 0 and e raised to 0 is 1, so we have c times 1, that is c. So the constant of integration c has the value pi, right? Now substituting c is equal to pi in the general solution, we can obtain the particular solution. So the particular solution is x cube over 3 times e raised to minus x square plus pi times we have e raised to minus x square. So if we take e raised to minus x square common, we have x cube over 3 plus pi, right? And we can also write it like this, e raised to minus x square over 3, and we have x cube plus 3 times pi, right? So this is the general solution, and this is the particular solution. So let us solve the second problem. So here we have x times y prime. Y prime is dy over dx. Then we have y, and here we have minus 3 times e raised to x, and this is equal to 0. And here the initial conditions are when x is 1, then the value of y is equal to 0, right? So let us first write this equation in this form. So we can take x dy over dx plus y, and taking this term to the right hand side, we have 3 times e raised to x. Now dividing both sides by x, we have dy over dx plus 1 over xy, and here we have 3 e raised to x over x, right? So now we can see that this equation is similar to this one, dy over dx, then we have py, and p is given by 1 over x, which is obviously a function of x, and then q is given by 3 e raised to x over x, and both are functions of x, right? So this equation is a linear differential equation of this type, and the order and degree of this differential equation are both 1. So let us find out the integrating factor. So the integrating factor is given by e raised to integral p dx, and here we have integral p dx. P is 1 over x, and here we have dx. Now the integral 1 over x is the natural log of x, right? And e raised to natural log of x is simply equal to x, because we know that e raised to, or in general we can write a raised to log of say x, and here the base is a. This is equal to x, right? So now the integrating factor is equal to x, and here we can see that if we write this expression in this form, we have e raised to log, here the base is e, and then we have x. So this expression is similar to this one. So the value of a is e, right? Okay, so now the general solution is given by this expression. So we have y times integrating factor, which is x, and then we have integral q times integrating factor. Q is 3 e raised to x over x, and then we have the integrating factor, that is x, and dx, and c is the constant of integration. So we have yx, and here this x and this x get cancelled, and we can take 3 outside the integral. We have e raised to x dx plus c. Now we can write yx 3 times the integral e raised to x, which is e raised to x, and c is the constant of integration, right? And we can also write this expression as y is equal to 3 over x e raised to x, and then we have c over x, right? So this is the general solution of this differential equation containing this arbitrary constant c. So now to get the value of c, we have to make use of these initial conditions. So here we are given x is equal to 1 and y is equal to 0. Substituting x is equal to 1 and y is equal to 0 in this equation, we have y is 0. Then we have 3 over 1 e raised to here we have 1, right? And then we have c over 1. So we have 0, and this is simply 3 times e plus c, and the value of c is given by minus 3 times the exponential number e, right? So this is the value of the arbitrary constant c when x is equal to 1 and y is equal to 0. So substituting this value of c in this equation, we have y is equal to 3 over x e raised to x, and then we have minus 3e over x. So this is the particular solution of this linear differential equation. So we can also write this expression as 3 over x, taking 3 over x as common, and we have e raised to x minus e, right? So y is equal to 3 over x times e raised to x minus e is the particular solution of this differential equation.